So back in 2017, 8 researchers at Google published a paper. They gave it this clever title, borrowed from a Beatles song. And little did they know, this one paper was about to become the blueprint for all of modern AI, kicking off the revolution that we are all living through right now.
So just how big of a deal was this? Well, to put it in perspective, this single paper, Attention is All You Need, has been cited over 173,000 times. In the world of academic research, that number is absolutely insane. It's legendary stuff. So what was the big idea? What sparked this incredible firestorm?
Well, the authors didn't waste any time getting to the point. Right there in the abstract, the very first paragraph, they lay it all out. A new, simple network architecture, the transformer. And the keywords here are simple and solely on attention. This wasn't just some small improvement. This was a total game changer. They were tearing up the old rulebook.
Now, to really get why this was such a massive breakthrough, we need to take a quick trip back in time to see what the world of AI looked like before the transformer. It all came down to a fundamental roadblock, the one-word-at-a-time problem.
You see, for decades, pretty much all language models worked sequentially. It started back in the 90s with things called recurrent neural networks, or RNNs. They would read text one token at a time. You can just think of a token as a word or maybe part of a word. By 2014, we had these more powerful models for translation, and by 2016, even Google's best model was this super complex system that still read everything in order, word by word.
And this one-word-at-a-time approach was a huge bottleneck. These RNNs would try to pass a kind of memory from one word to the next, but it created 2 massive problems. First, the memory was terrible. By the time the model got to the end of a long sentence, it had pretty much forgotten what happened at the beginning. And second, it was just slow. You couldn't just throw more computers at the problem to speed it up. It was fundamentally limited.
So AI was basically hitting a wall. The old way was just not cutting it anymore. The entire field needed a breakthrough. And that breakthrough came from a surprisingly simple idea: attention. Which of course brings us to the big question. So, what exactly is attention?
At its core, attention in AI is a lot like our own attention. It's really just a way for the model to give certain parts of the input more weight or more focus than others. Just like your brain is doing right now, picking out the key words I'm saying to understand the meaning.
Here's another way to picture it. Think of it like a soft mask that the AI places over the sentence. It highlights all the important stuff and kind of dims out everything that's less relevant. But if you really want to get down to the nuts and bolts, mathematically it's actually incredibly simple. Attention is just a weighted average of all the inputs. That's it. That's the secret sauce. You take everything in, but you decide that some pieces of information are just more important than others.
For instance, let's take a simple sentence. Please go to the store and get some milk. The model learns to assign a weight, or a score, to each word. And you can see here, words like milk, get, and go get high scores. Meanwhile, filler words like the and to get almost nothing. The model's final understanding is a blend of all the words, but it's heavily tilted towards the ones that actually matter.
Okay, so the model is giving words a score. That makes sense. But how? How does it figure out which words get a high score? This is where we get into the real engine of the transformer, something called queries, keys, and values.
And there it is, the famous formula from the paper. Now, I know what you're thinking. That looks like a whole lot of complicated math. But trust me, the idea behind this is way, way simpler than it looks.
So we are definitely not going to dive into a linear algebra class. Instead, let's just use a really straightforward analogy to break this down. Think about using a search engine, right? The thing you type into the search bar, that's your query, or Q. It's what you're looking for. The search engine then looks at all the possible videos or websites and it checks their titles and keywords. Those are the keys, or K. Then, based on how well the keys match your query, the engine shows you the actual items, the videos, the documents. Those are the values, or V. The final result you see is just a mix of the most relevant values, all weighted by how well they matched your search. That is exactly what's happening inside the AI.
So, what about that weird little square root thing in the formula? Well, that's actually a super clever but simple trick. See, as these models get bigger and bigger, the numbers inside the calculations can just explode and get out of control, which makes the whole thing unstable. That little scaling factor, it's like a pressure release valve. It just keeps all the numbers in a stable range, which is absolutely crucial for training these enormous models.
All right, so that's the main engine. But the researchers didn't stop there. They added a couple of really important upgrades to make this whole system even more powerful.
We're talking about two major bells and whistles here. The first is called multi-head attention, and the second is a really clever idea called positional encoding, which solves a brand new problem that this architecture created.
So first up, multi-head attention. The idea is, instead of just calculating attention once, why not do it several times all at once, in parallel? Each one of these parallel calculations is called a head, and this is what makes it so powerful. One head might learn to pay attention to grammar, another might track who's doing what to whom, and a third might focus on the overall sentiment. It's like having a whole team of specialists looking at the same sentence at the same time.
Okay, hold on a second. If we threw out the one word at a time method, and we're now looking at all the words at once, how in the world does the model know what order the words are in? I mean, the dog bit the man is a very different thing than the man bit the dog.
That is the million-dollar question, and the solution is just brilliant. It's called positional encoding, and it's basically an ingenious hack. Before the model does anything, it adds a unique mathematical signature to each word. It uses sine and cosine waves to create a sort of digital fingerprint that doesn't change the word's meaning, but simply tells the model, hey, this is word number 1, this is word number 2, and so on.
All right, let's put it all together. We have our core attention engine, we've supercharged it with multiple heads, and we've added a clever trick to keep track of word order. So what's the big payoff? Why did this specific combination become the engine for the entire AI boom? This one table from the paper tells the entire story. Look at the old RNNs. As the sentence gets longer, that's the N. The number of operations goes up. More words means more work. But for the transformer using self-attention, it's O of 1. It's constant. It doesn't matter if the sentence is 10 words or 10,000 words, it takes the same amount of time to compare any two words. And that was the key that finally unlocked massive parallel processing for language.
And the rest, as they say, is history. 2017, the paper drops. Just 1 year later, boom, OpenAI releases the first GPT. Fast forward to 2022, and ChatGPT explodes onto the scene, changing everything. And today, that same core transformer idea is behind AI that creates images, understands speech, and even controls robots.
So here's the ultimate takeaway from all this. The true genius of the transformer wasn't just that it was a smarter algorithm. It was an algorithm that was designed from the ground up to perfectly match the hardware it runs on. For years, we had all this incredible parallel processing power in our GPUs just waiting. The transformer was the key that finally unlocked it.
So, attention was that one simple idea that allowed computation to scale in a way no one thought possible. It kickstarted the entire revolution, which really just leaves us with one question, right? What's the next simple idea gonna be?